Good afternoon. Well, Garrett, thanks for introducing some things that I didn't put in slides, so awesome. It's good not to be the first, right? Maybe quick background on me, because that will help understand some things. I'm originally from Europe. I actually got my advisor sitting in the room over there. And if you know things in Europe, expectations are as high, but it's a lot of let loose. Do it on your own. Right, that's how actually I got through my degrees. It's like, okay, shoo, there you go, right? I can't do this on the undergrad level. I tried to implement this a little bit on the graduate level. There's independence, and there's time management skills coming with this as well, right? But okay, what's in it for here? This thing moving, let's see, click 1, 2, 3. Yes, there we are. All right, so it's rheology. So I'm gonna give a quick intro into the class to see where we're at, right? And I will discuss what the errors are in cement-based rheometry. I'm not the purpose to do this in a technical way, but to highlight what I think they should carry away in the future. What I think they should retain from the class. It's education, what you remember after you left school, right? That's what I wanted to have. And then we'll introduce a project, part 1 and part 2. And we'll be very clear why part 1 and part 2. So the class itself is called Understanding Rheology of Cement-Based Materials. Target audience, grad students. In our case, it's a 6,000 level class. It's the highest level class we can have. Undergrads can only get in very exceptional circumstances. So the audience is pure 100% grad students. So full semester, I had 9 in person. I had also 4 online. So I had a distance component to it as well. So that forced me actually, because we've done this class before, to flip the entire classroom. So anything that I felt was lecture related was pre-recorded. And then we had discussion sessions, Q&A, and so on to spend the time in the class. Topics-wise, so first a quick introduction is 2 week long, that's it, right? To put us on the same page on what rheology actually is. And then we spend about a month on nothing related to cement and concrete. It's suspension rheology, it's the physics, chemistry, anything that can help us explain the behavior of cement-based materials. So by here we're starting, and it's a fall class, right? So we start to be somewhat by the end of September. We're 6 weeks in, right? And then we start applying everything. Now, thanks to chapter 2, chapter 3 becomes very easy. This implementation is like, okay, we've seen this, this explains this, and so on. And then chapter 4 is measurements. And that's what the project is focused on, right? So what are the tools, what are different procedures, what are calculations, and especially how things can go wrong. Because if you think that rheometry is a simple tool where you click on a button and you get results, well, maybe you should take my class as well, right? And then chapter 5 is what I call complex phenomena. That's where I start sweating on things, because that's the edge of my knowledge as well. I want to give them a few really complex things in the field of rheology based on some of the concepts we've seen before. But okay, we'll focus on chapter 4. Evaluations, that's what I said, European style. I got 2 exams. Right, mid-semester exam, final exam, because of distance part, it's with preparation at home, but then they have an oral defense. So we're talking European style, right? And by talking to students, you really know if they understand yes or no, 100%, no, 99.999, right? And the half of the grade is a project. European style, let them loose, right? But the project focus, like majority of the class, is inside the project. So what's happening with cement-based rheometry, right? So what's rheometry? Rheometry measure, in our case, fresh properties of cement-based materials in a somewhat scientific manner. Or we think it's scientific, let's say it that way, right? The expectation is this behavior, fresh shear stress versus shear rate is linear, it has a yield stress, it acts like toothpaste, and it's thixotropic, so it acts like ketchup, which is really complicating the measurement, because now your properties are dependent on how you measure. Measurement procedure influences results, right? So that's one. And then we have constituents. Whatever we change in cement-based composition or in concrete composition follows, to some extent, this graphic from literature. That's the Wolovic brothers produced this one based on extensive tests. And I'm highlighting 4 because that's the 4 we've used in the last project. We got water, increased water, everything because we're fluid, you're fine. Add a water-reducing agent where your yield stress is going down, your viscosity stays about normal. Then you add silica fume, and depends if you continue to disperse, yes or no, but typically everything goes up. And fly ash, we don't know, because fly ash is the tricky one because it depends on so many things, right? Now, where's the source of the errors coming in? Well, it's from this thing, and it's a blunt referral or a blunt putting this Rheolum report out of here. It's a state-of-the-art report that's created by the Rheolum Committee on measuring rheological properties of cement-based materials. That's where I, together with a couple of colleagues, have been able to highlight those measurement errors and coming and dedicating a whole chapter in the report to us, right? And I used that report for the first time. I used to do it differently, but I used that report for the first time because it just came out like a year and a half ago in a pre-recorded lecture that took about an hour for me to walk through. So that's an instructional thing that you get it there. It says what's the source of the error, what's the consequence, and how can we, if possible, detect and prevent it. And this is more or less a summary table we have in here. And again, I'm not going to look too much into detail on all of these. But I want my students to especially get the 4 in the red boxes. Right? There's some easy ones. Likelihood for the class to happen, yes or no. Right? How do we detect it and what's the correction? We instruct this in November. This is getting around the Thanksgiving period. As you will see, the project is well going on already in that case. All right, so here's the project, part 1 and part 2. So we post this end of September. So they have more than half of a semester left, and there's due early November, and it coincides with chapters 2 and 3, so I haven't seen nothing on measurements yet. What we use is our Par MCR 72, and that's key. Because for those working in rheometry, typically your equipment is extremely sensitive. And even if you look at it the wrong way, it will break, cost you $50,000 to repair, and so on. So you don't want to use this or have students use this independently. That's a little more tricky. Well, we get one that can handle a little bit of abuse. Let's say, well, let's not exaggerate. That's what I try to tell the students. It's, still don't hit it, but it should be okay if you manipulate it at some point, right? And we give them a quick training on device functionality as well, but that will be one of the conditions coming in that I'll discuss later. Because we had 13 students, put them in 4 groups, and then measure the effects of a variable, the 4 we discussed before, and repeatability. That's another concern, right? And we tell them measure yield stress, measure viscosity, measure thixotropy over an hour. And again, at this point, they have no clue, right? So I'm just telling them, measure. Try. Figure it out. Right? And what they're supposed to submit, small report with their procedures, the results, the calculations, interpretations, conclusions, and so on. And their grading, well, they get no grade yet. Because it doesn't matter. It's their precursor for part 2. Right? So, mistakes all the way around. Part 2, then, is what we call the rectification. Now, how are you going to correct, right? We start early November. We just started the chapter on the measurements, right? We're already starting to look into calculations of properties and so on. And the goal of the project now, which is the 50% of the total grade, is to identify the correctors and correct the errors you've made, right? So what's the error? What's its cause? Tell me. What's the consequence and the effect on the measurement? Tell me, right? So they haven't done a single measurement yet in addition. Recalculate if it's calculation based. Show me what the new numbers would be. Advise on if, because some is really difficult to actually recalculate, so then tell me, okay, what do you want to do differently in your experiment? And then suggest a new procedure and try it. But once you try your new procedure, you evaluate again compared to all of everything you know now. I'm allowing you to do one more adjustment. And the reason is, if you have a perfectionist, they're going to try to make it perfect. And the issue is, sometimes you can't make it perfect. It's not working. There's some materials that can't be measured. There's always something going on, right? So that's to limit the students. They're like, look, you make this one additional modification. If it's still not according to your desires, just tell me what you think is still happening, how you would correct it. But don't do it again, because otherwise we'll have a traffic jam at the rheometer 2 days before the project is due as well. Right? We only have, well, we actually have 2, but we can only use 1. Right? So try it out on the measurement, on the reference, and then tell me the effect you have on your variable. Is it going the same way? Is it to the same extent? And so on. So how does your observation of the effect of water, plasticizer, and so on changing based on this new either measurement or interpretation or both? Right? Then submit Excel files, which is a nightmare as an instructor. But submit the Excel file so I can really follow what you do. Right? And I'll go dig deep and to see, okay, how you get from column A to column Z and so on. We'll look into it. And then record a presentation. Again, I got 4 distance students, right? Record a presentation with the group on what lessons you've learned. And there's a question on the final exam that actually allows me to discuss one-on-one what you've learned from the project. right? So there's another one-on-one communication going in there as well. And you're evaluated based on the corrections, the assessment of your errors, understanding of the consequences, and then discussions on repeatability. And there's no judgment on perfection, but again, it's like to which extent do you understand what's going on. So here's my table, the same table with the errors I have. So we have 4 groups going on. 4 groups, we considered, so of the 4 groups, on the 4 errors I really wanted to take home, or for them to take home, they all considered the error. They looked at it. They said, okay, it is an error, we need to change something. And apart from the particle migration, which is by far the most complex phenomenon we have, all the groups really looked into, about one group still make mistakes on the calculation over here, right? But all the groups considered all the errors apart from, or at least tried to make it adequate change into that, right? And again, the particle migration is the real tricky one going in there. All right, so lessons learned. Pros, it's very effective. They really, if they have a hands-on, they learn, right? I can teach them 3 hours about measurements. I can teach them 7 hours about measurement. I can teach a whole semester about measurements. They learn better this way because now they have to do it, right? It's not excessively demanding in terms of time commitment. And again, to me, my opinion, a grad level class is for them, is a support towards their PhD or their master they're pursuing. That's my philosophy on that, right? So I'm not going to overload them too much in it, right? So it's an extension of theoretical material, and then, you know, without major assistance, they can handle it. And again, the grad students, and some of them have expertise in that. Question is, can we extrapolate this to other topics? That's a big question mark. I felt that they have put in a significant effort in their work. Right? It's not something that's like, hey, let's do this last day before the project is due. No, there was communication. There were tons of questions coming in. It's like, hey, we tried this. What about this? What about this? So there's a lot of interaction going on a voluntary basis, nothing forced, just voluntary. And very good perception of the project from at least the ones that were in person. Now, some cons. You need the equipment, right? If you don't have the equipment, that gets a little more tricky, right? Students need to have a certain level of maturity, and that's why it's grad students, because with undergrads, I can see this happen. Well, one, the topic wouldn't work, but it become a lot more difficult, I think, to motivate them. Now they had this automatic motivation. Even some of my students were studying the rheology of black sticky stuff, and didn't want to know about concrete, but learned about everything took some things away from their own research as well. The outcome is strongly dependent on how much the students are involved. So again, we got on the better side. And then here's a risk, right? Some students may dominate the group. That's possible. And the reason, so the groups are split up. They all had one distance student and one person who has some expertise in measuring, and then 1 or 2 others. So it really depends on how your class population is structured. So we have people that knew, in some extent, how to do measurements. Maybe they knew the wrong way, but they knew something, right? And I had to tell them explicitly, it's like, be stupid. Pretend you don't know. Because otherwise you have the risk. It's like, yeah, but you know, I know we got to do it this way. I know we got to do it this way because this can be wrong, 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 wrong. I'm like, yeah, part 1 of the project, go ahead and make it wrong. You know, if you have knowledge about procedures, go the other way. Try to make it as wrong as possible. So then you have more things to correct in part 2, right? And one of the bigger things was a challenge to include the distance students because they can't be physically there during the measurements. I tried to have the students live stream or record the procedures, but that got a little more difficult, right? So in the evaluations that we received afterwards, there were some suggestions on how to improve things and so on. We'll consider this to see, but that's been the bigger challenge, is how to include those distance students to a better extent in this pretty much a hands-on project, at least partially, so that was a challenge. So that's it, that's all I have. Correcting your own mistakes, best way to learn. Thank you.